Welcome to this high-stakes explainer. Today, we're not just cooking, we're undertaking a classified mission. Our objective? Culinary civil engineering, the 12-inch Nacho Tower protocol. I am incredibly excited to guide you through this, because constructing a freestanding, 1-foot-tall Nacho Tower isn't just about throwing some snacks on a plate. It's a precise, rigorous exercise in structural integrity, material science, and thermodynamics. Look, most home attempts end in an unappetizing, wide pile of disappointment, but we're going to approach this with the exactitude of building a literal skyscraper.
So here's the ultimate challenge for us today. Can you engineer a 12-inch Nacho Tower? We're talking about a massive 1-foot vertical payload. I mean, anyone can make a flat, single-layer plate of nachos, right? But elevating those carbohydrates straight up into the air without the whole thing toppling over, that requires some serious architectural prowess. It's an all-out battle against physics. So are you ready to test your skills?
Because here is the fundamental reality of our mission today. You need to beware because lateral shear forces cause catastrophic structural failure. If you just pile chips into a massive mound, gravity and these lateral shear forces are inevitably going to rip your creation apart. Think about it like an avalanche or a mudslide. Unanchored material stacked way too high will always seek the path of least resistance outward. Piling simply doesn't work at a 12-inch vertical scale. Gravity absolutely demands a radical architectural solution here, and we cannot afford a collapse.
To prevent that collapse, we initiate Protocol Alpha, the blueprint and the formwork. Consider the sheer ambitious scale of our objective. A standard order of restaurant trash can nachos usually utilizes a number 10 commercial food can. That maxes out at a meager 7 inches tall. But our objective? A full 12 inches. That's nearly double the standard height. To achieve this, ordinary restaurant techniques simply won't cut it. You actually have to procure a custom, extra-tall stainless steel cake ring measuring exactly 8 inches wide by 12 inches tall. This heavy-duty piece of hardware is literally the only thing standing between a perfect cylinder and utter chaos.
Now, how do we prep this formwork? First up, you need to line the inside of that stainless cylinder with parchment paper or, ideally, a food-safe acetate cake collar. The crucial point here is that the acetate collar prevents the melted cheese from welding to the metal mold. If you skip this step, the cheese is going to bond to the steel, and when you try to extract the tower later, you'll literally rip your creation apart, leaving half of your ingredients cemented to the ring. Finally, place this cylinder securely in the center of a heavy-duty, parchment-lined baking sheet, just to anchor the entire operation.
With the mold secured, let's move right into Protocol Beta, load-bearing materials. First, we have our aggregate. We're talking thick-cut, restaurant-style fried masa chips. You absolutely cannot use thin cantina-style tortilla chips here. Think about the massive gravity involved. The bottom layers of this tower are going to be bearing a multi-pound payload pushing down from above. If your aggregate is weak, those lower chips will easily snap under the extreme weight, and the base will shatter into a soggy, unrecognizable sediment. And that's going to cause the entire tower to tilt and fall.
Next is what our source brilliantly refers to as thermal rebar. What's truly fascinating here is how we're treating cheese exactly like industrial concrete. It's a specialized 2-part lipid system. First, you need 4 cups of a shredded Monterey Jack and cheddar blend. This is vital because it actually hardens as it cools, acting like reinforcing steel to provide real rigid structure. Second, you combine that with 2 cups of liquid queso dip. The queso provides this gooey, void-filling matrix that gets into every single microscopic gap. Together, these 2 lipid types will completely fuse the entire structure together.
Rounding out our materials list, we have our mortar and our payload. You're going to need a high-viscosity anchor, which means 2 cans of warm, thick, paste-like refried beans. Then, 1.5 pounds of seasoned ground beef or shredded chicken. But pay very close attention to this absolute mandate. The meat must be drained completely of grease. This is non-negotiable. If you introduce excess liquid meat grease into the structure, it'll seep downward, turn your crispy aggregate into a mushy paste, and utterly destroy your foundation.
Now that our materials are fully prepped, we enter Protocol Gamma, architectural layering. Let's walk through these rhythmic building steps. And remember, above all else, you have to build horizontally. Why? Because angled chips slide past each other under compression, creating internal fault lines. So, step 1, lay a flat, horizontally overlapping chip foundation at the bottom of your mold. Step 2, spread a heavy, uniform layer of those warm beans. This cements the base level together. Step 3. Add your thermal rebar, a handful of shredded cheese, and a drizzle of queso, followed by the meat payload. Now don't overpack the meat. The cheese actually needs to physically touch the chips to fuse them. And step 4, press down firmly on the next layer of chips. You want to compress out any empty air voids before repeating the whole process.
So how many times do you have to repeat this exact sequence of chips, beans, cheese, and meat? 6 to 8. Yeah, 6 to 8 times. That is the massive number of layers required to painstakingly reach the 12-inch apex of your cylinder. It really is a true architectural feat.
Which brings us to the most suspenseful phase of this entire explainer. Protocol Delta, thermal fusion and extraction.
You're going to bake this massive cylinder at 400 degrees Fahrenheit for exactly 15 minutes to initiate the phase change of the cheese. But you must heed this warning carefully. If you pull the mold off immediately, the boiling liquid cheese will act as a lubricant and the tower will collapse. Just let that sink in. You have to execute a strict 3 to 5 minute thermal rest after you take it out of the oven. This mandatory rest period allows the boiling cheese to cool slightly and firm up into a structural cage. Skip the rest, you get a devastating landslide.
Once properly rested, follow this extraction protocol. This is literally a bomb defusal moment requiring a 2-person lift. You grab the outside of the mold and lift it perfectly straight up, completely perpendicular to the baking sheet. Any angle or wobble at all will shear the tower. Then, and only then, do you garnish immediately with your cold, wet ingredients, your sour cream, pico de gallo, and cilantro. I really must vehemently warn you, never bake these cold, wet ingredients inside the matrix. Their cellular water will steam during the bake and turn your beautiful, crispy core into a soggy, unstable mess.
But wait, our engineering debrief isn't quite finished yet. I need to present the Red Team report, Avoiding Core Temperature Failure.
Consider the ambient heat of your oven, 400 degrees Fahrenheit. At 400 degrees, the oven will easily melt the cheese on the top and the outer edges that are physically touching the hot metal mold. However, the geometric center of a densely packed 12-inch carbohydrate cylinder acts as an extreme thermal insulator. The heat simply cannot penetrate deeply enough in just 15 minutes of baking. And what that means is the absolute core lacks structural fusion entirely.
So, what's the ultimate countermeasure to this heat distribution failure? 160 degrees Fahrenheit. All of your internal wet ingredients, the beans, the queso, the meat, they all must be preheated to at least 160 degrees before you even begin layering them into the mold. Seriously, do not build this tower with cold ingredients straight from the fridge, or your core will remain a cold, unfused liability. And that center, it'll give out the exact moment the mold is lifted.
So, after digesting all of these protocols, I leave you with this final, provocative question. Will your 12-inch tower stand firm or succumb to shear forces? You now possess the blueprint, the material science, and the thermal countermeasures to pull off this incredible feat of culinary civil engineering. The blueprint is yours. The kitchen awaits. Good luck out there, engineers.